In this video, we'll talk about the fifth assumption in a simple linear regression model, which is the assumption of homoscedasticity or constant variance. Okay, but to get to that sort of measure of variance, or in other words, variance is just a measure of some sort of dispersion or spread in our data. We're basically interested in not the data here, but really the dispersion and spread in the sampling distribution of our estimators. Okay, so really we are interested in these guys here. So variance of beta 1 hat and variance of beta naught hat. Okay, so you're going to use the variance and ultimately talk about a standard deviation. Now you can take a look at two distributions here, and clearly you can see that the probability distribution function for W2 is more spread out than the probability distribution function of W1. Okay, and this is this is visual, but even if we were to calculate some measure of dispersion, we would find that this was more spread out or displays more dispersion or variance than the other distribution. So this brings us to this fifth assumption, this idea of homoscedasticity or constant variance. So homo means, okay, here constant, we're talking about variance. Okay, so what we're really talking about and want to emphasize is this variance of the error term given x. So we basically want to understand, does our error have the same variance given any value of the explanatory variable x? Okay, and our assumption says that this should be equal to a constant, right? So here you see sigma square is a constant. It is not varying with the values of x. Okay, so if we wrote out, for example, variance of u given x equals sigma I square, then this would violate the assumption of homoscedasticity. We're basically, when we write down this subscript I, we're basically saying we're allowing the variance to vary with x. So here we are allowing the variance to vary with x. Okay, so this is heteroscedasticity. Okay, let's try and understand how can we get to understanding what the variance of y is for a given value of x, okay, and if that is constant. So let's start with the last assumption that we talked about, which was this fourth assumption that the expected value of u given x is 0, okay. And if we assume that there is homoscedasticity or constant variance, we can write down this expression that the expected value of u square given x is equal to some constant, which is equal to the expected value of u square. And I'll tell you where that comes from. So let's try to perhaps get to this expression. So the variance of u given x can be written out in terms of the formula. We'll use the expectations operator here. So the expected value of u square given x minus the expected value of u given x whole square, right? So we can write out the variance of u given x in this way. This is just the definition. But we know that this itself equals 0, right? That's what we said here. This is equal to 0. So this entire expression let me use a different color here, this entire expression goes away. This becomes 0. So what we're left with is this expected value of u square given x, right? And this is what we call sigma square, okay? That's why we're saying that the variance of u given x can be written out in this form, okay? And basically, if this is a constant, right, we don't really need that conditioning on x. If this is a constant, it doesn't really depend on x, right? That's why we can write this equal to expected value of u square. Okay, now the next thing is, well, how do we get to the variance of y given x? So remember that the variance of y given x, because this is our simple linear regression model, the variance of this of the left hand side would equal the variance of beta naught plus the variance of so this should be beta naught conditioned on x, okay, plus variance of x given x plus the variance of u given x, right? So notice that if we were thinking about the variance of a constant given x, that is just going to be equal to 0. The constant is this right here is just going to be equal to 0. Similarly, the variance of x given x is just 0, right? So what we're left with is the variance of y given x equals the variance of u given x. Okay, so we come up with that same expression and we said the variance of u given x is equal to sigma square. So therefore we can say the variance of y given x equals sigma square. Okay, so in other words, the average or expected value of y is allowed to change with x, okay, which is what we want. We really want that y should be allowed to change with x, right, when we're thinking about the variation in y. But the variance itself does not change with x. So there's a difference between wanting the expected value of y to change given x and wanting the variation y, the variance in y to change with x, right? So we want to allow for this to happen, but we do not want that this changes with x, okay? So this we want this to be equal to some constant. It should not be with a subscript I, okay? So this not, let me delete the I here, okay? So this is supposed to be equal to some constant. So let's take some examples and try to understand this. So let's assume that we were interested in looking at how does income affect saving behavior, okay? So we might be interested in this question for many reasons, all right? If we would think about what determines savings, it is really income is one of the biggest factors that affect savings, right? Now we would expect the value of beta 1 to be greater than 0, right? So we on average expect that a family, the family savings, if this is family savings or individual savings, these would increase with income. So as your income goes up, savings also go up, okay? But if we impose this last assumption that we're talking about, then we might be saying that the variation that we observe in saving, given any level of income, is constant, okay? And this might be very restrictive. You might actually expect that the variability in saving behavior is much higher at higher levels of income, right? So if we were thinking about what is the variance of saving for people who have, for people with income equals $20,000, right? Is that equal to the variance of savings for people who have income of 200,000, let's say? You might think, well, this does not look like this is correct, right? We might actually have, this might be actually higher. This variation right here might be higher than this, okay? So in other words, if this does not equal this, then this is not equal to a constant, right? This is different. This is lower, this is higher, and this is really varying based on what our income is, okay? So there might be, if we were trying to estimate a model like this, the fifth assumption of homoscedasticity definitely seems like, would be violated. Okay, now you can imagine that if you had some sort of a, if you had some sort of a formula, I'm not going to go over the example, but really if you have, if somebody wrote out the variance of y given x equals sigma square over x, as soon as x appears in the equation, this is displaying heteroscedasticity. Okay, this is not homoscedasticity. So this is non-constant variance. Based on the value of x, this expression is going to keep changing. Okay, so there is, so basically your simple linear regression 5 is violated in this case. Okay.